So we're cleaning up a little bit, and I just realized I've made a big mistake because I kind of realized that there's a reason why this is called half turns, and it's because it's specified in terms of sort of the exponent of the Z Powergate. And if I just go to the circ documentation, I'm guessing that's not an angle. Oh, that's G. No, exponent T. Oh, so that is the thing here. Okay, so this is already in terms of, yeah, okay. So this is this D here. So I'm totally stupid. But I have had a really stupid idea, which is actually I think a good idea, which is I wanted to kind of make a bit of an animation, an animated version of these where I kind of explore sort of how the landscape of like you know a two-dimensional a circuit with two parameters um, kind of evolves, and see if we can find like a parent plateau or something like that. I'll almost like even just leave it live streaming for like 5 hours and see what happens. So just wanted to have like I just made those here, and I wanted to kind of clean these up a little bit because so this is for 3D projections, but I have a messy thing in here. So with the circuit construction, so uh, I want to kind of get rid of these things. So first of all, let's have a more generic way to build circuits in a way that it's kind of like, so let's just have like, you know, insert cell below, and so this is going to be circuit construction, and then yeah, at the end I just want to print the circuit, right? We're going to have alpha and beta, and we're going to have like uh, just length be. Is length used anywhere else? It's used in here. Okay, but it's used in here, so it's part of the parameter, so that's fine. Um, so length length will just be 2, so we're just making like a you know just like a row of qubits, and we're gonna have two parameters, alpha and beta, and so we're gonna create this circuit, and then we're just gonna add the measurements at the end. So that's what we're gonna do. Row layer alpha. So I can specify length. I can specify, okay, for, yeah, okay, cool. I like it. So create a circuit, and so circuit's not defined. Just come on. Can I import this stuff just like everything at the very beginning? Makes more sense. So I'm gonna cell, just edit, delete cells. I'm gonna need that later. Okay, so let's just like run these. I think this is really not needed. Edit, delete cells. So we're gonna just do these. By the way, I'm gonna remove the sweeping part. So that's basically the pre-processing um, before building like the 3D stuff. So actually that should all go. That should all go like. That should all. So these will be utilities. This is going to be the circuit construction. That's going to be like the 3D plotting. And so this is going to be, okay, I'm going to leave the imports in here. I'm going to have like simulation and pre-processing. So I'm going to have these. Oh God, I lost that part. No. Oh, come on. Don't tell me I've lost that part. Mm. Oh, damn it. How can I? And that's probably just. Oh, unsaved changes. What if I just open it again? What's the state I get it into? Oh, there it is. There it is. Simulator. Let's copy that stuff and let's paste it in here. Cool. So we're creating a simulator, we're creating this sweep, and then this is just what's wrong, you know? It's like, this is just from 0 to like, you know, like 100 or something. It can be whatever. It doesn't have to be like. We're not. It's like between 0, I would say, because it's, so if it's 0, if it's 1, it's pi, so from half turns to complex number on the unit circle. The t in the gate t limits how much the eigenvalues of the gate are scaled by. For example, I'm faced by -1. So these numbers actually can be negative. Global shift. So you can also play with the global shift. What is the global shift? Starting with an angle in half turns as returned by the gate's eigencomponents method. Shifting the angle by a global shift. Scaling the angle by exponent. Converting from half turns to a complex number. So you could even play with a global shift, but I'm not going to go that far. So I'm going to, what if we just like start at like, I don't know, -2, -2, -2, and then like +2, +2, and so we do this like in like 100 steps and 100 steps. So this is the sweep that we're doing, and so we do like 10,000 things. So and then we have the alpha. So this part is just basically building the alphas and the betas. And then what we do is we run the circuit. Each time like 100 times, because otherwise it just gets too big. But I can also do 10 times, just for performance now. And then we're getting the values. And we're calculating, so this is what I was having problems with, like calculating the, that we're going to fix this now. So calculating the eigen values of that. But that's maybe something I can encapsulate into another part where I take, because these are the eigenvalues that I want to have. So why don't I just have like a sort of another function in here? What would we call it? We'll call it like calculate eigenvalues. So give you the results and the eigenvalues, right? And then it just returns these array. So it returns e values, right? So basically, so I'll be more like expectation value. So this would be like def expectation value and it gets like, so it gets the results, and it gets the eigenvalues. And what it does is it returns e values. Okay, so you need these, and this is what we're doing here when we're creating the circuit. We're also going to define circuit construction. So basically, so we're going to define another component of it that will be like, oh, what am I doing? So this is going to be like a what are the observable that we want to define? You're gonna fucking kidding me. Why doesn't these get copied properly? So this is the basically the values. So we're gonna find these in here, and the circuit, right? And then what we have is the expectation value. So here we're just giving it the results and the eigenvalues. And there we go. And now, cool, scatter alphas values, blah, 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 blah. So now this is so the 3D plotting is about these, right? So you're simulating, you're calculating the values, and you're and then you're doing the figure. Cool. And that's what was working here, but that's not what's working for me. What's not working for me is this part here. So now we have these. So basically I can delete these cells. That's much simpler. So we run these imports, we run these sort of utility functions, and then we say, okay, now we do these. Maybe I should just also have that as the insert cell both, and I'll just should just have these in here and say I want the eigenvalues of these, right? And so and now what I want, and I kind of I'll have more, like I have other things in here, right? And so what I want to have in here now is in this other cell, I'll create a circuit that basically has, so this circuit now just would have like a measurement, and we don't want that, so we want the circuit to be like, for example, a like a rotation of Y layer. See, maybe I shouldn't just use the layers if I don't want to have layers, right? So if I just want to have these, I can as well just say append how do I do these circuits? How do I build circuits? I append this and I tell it the qubits it's working on. The exponent. Mm-hmm. Mm-hmm. So how is it doing it? It's doing yield a rotation, and then you call the qubit. Okay. Mm-hmm. So what if I just say, well, uh, that's operation one, right? I think I can just call it like on. I think I can just do like these, right? So okay, I just say um, these on qubits 0. I think I can I just do like that? Append. Circuit append. Half-turn is not defined. Yeah, that's true. So this is alpha. What? Non-type. Append. So how the heck you do that? That's on. Yes, that's on. I mean, just don't fool me. It's append. Oh, don't tell me. Don't tell me it's okay, I can get rid of this. Don't tell me it's circuit append. Append. Blah blah blah. Circuit append. Maybe I gotta do it this way. Circuit append. What is wrong with these? Circuits append. Yeah, that's what I'm doing. Okay, but it's not. Okay, so you don't do these. Maybe that's the idea. Okay, you don't do that. You don't do that. Okay, there you go. So we'll do these with beta and qubits 1. So okay, so we're not going to use any of the x 1. So we have this circuit. So we have this circuit. Cool. And now we have the circuit. We have these stuff. And so what do we want to do with these? What we want to do is we want to plot. So we're doing the 3D plotting stuff in here, and then we get the simulator. We get the sweep set up. we get the parameters, the alphas and the betas, and then we run the simulator 100 like 10 times per element of the sweep, and then we do the plotting, which basically so we calculate the expectation values and then we do the plotting. Now the expectation values are going to break. Yeah, that's basically going to break, right? Because this counter stuff, like this is what's not working. So how do we fix that? This is what's not working. So what is R? So let's go here and print like print R and print eigenvalues and see what happens. Because that's the problem. Now I feel better. It's a bit better organized. And then so what will be cool will be to animate these stuff, right? So kind of do different like. Okay, so what is going on here? Okay, so counter. So that's what it is. That's the wrong thing that I'm taking a look at. So the 0 element 10 times. That's the wrong thing I'm taking a look at. You measure all the qubits, right? So it's not R. Well, what I want is because R is just is these, and I actually want the vector like, you know, equivalent to that, like. So I guess, yeah, I guess what I have to do is I have to first transform like the R as in like, so not like the histogram like that, but like getting the so maybe there's a way results. Maybe there's a way we can just take the results already like that. Batch results, simulation, results. Print results. So this is what I'm getting is the histogram, and what I want these into array form, into an array form. That's what I want. So basically, what I would have to do is so I'll have to create. So what I want to do is I want to do the array values, right? So the result values. So what I want to do is I want to do np array zeros. Keep forgetting numpy zeros. Shape. Something like this. Okay, cool. So I want them like these, and I want these to be like land of the eigenvalues, because I want eigenvals, because I want these to be like, yeah. And then what I do is I do basically for element in the R, so numpy iterate over dictionary print state. What the heck? So okay, so that actually, okay, that actually gives me the, should give me the, so the, it should actually give me the element. So what I would do is then like rvals element equals r element, exactly. And now I should just basically print rvals. That's what I want to print. And print the eigenvalues. So I'm just gonna, no, let that break actually. It's gonna make it easier to debug this thing. So, and then I just want to have that. So that should work now. I should see. Yeah, there you go. Cool. That's all. That's what I want to get. So now what I do is I do rvals like these, right? So, and shots. I should definitely do shots, and this should be shots, and then the expectation value here should be shots, and I should just define shots to be 10, and I should just say, you know, shots where 10, not 10 seconds, 10. Let's see what happens. Let's see what happens. What am I expecting to happen? What do I expect to happen, to be honest? These expectation values are appended and they're returned in here. Okay, it actually broke. Which is inconsistent with X and Y with size 10,000. Yeah, but it should be 10,000, so what is the problem? E values. So for each result, you do that. Expectation value, you put it there. So let's print, well, let's just print these, okay? Can I just print the 3 of them? Can I return like that? No, I probably cannot return like that. I just want to, sometimes just want to stop. Okay, but what's going to happen now? I should print the lens and not like the, yeah, that's just stupid. Lens, lens, lens. It's all 10,000. That's kind of good, right? So what's the problem now? Well, why? No, why have I put shots in here? Shots go here. That's the problem. That's all correct. Cool. Shots go here, my friend. Mm. Oh, what's wrong now? 3 are given. Expectation value. Didn't run this probably. And now this. Hmm. What am I expecting? I'm expecting to just see the 3D plot of these, probably. Of these two. Oh, fancy stuff. Okay. Oh, nice. Runtime invalid value encountered. Okay. Runtime warning. Oh, that's nice. Why it prints two things though? That's some nice. Okay, now it just might be working correctly. What if the circuit just is like an empty circuit? Let's just try that first. Let's see if that works. And yeah, it's just flat at 1. Okay, I like it. Now let's make that bigger. So first of all, let's make that less steps. First of all, is this still something that makes sense? Kind of. Shrink. We don't want this to shrink. Aspect. So can I? No, that's the color bar. Who cares about the color bar? The surface. Oh god, that looks just awful. And that's the projection, I guess, on the top, right? That's nice. Now, what do I want to do? I want to have so matplotlib figure size. So what is it we have here? So we have the color bar, there's a color bar, blah blah blah, figure, plot figure. Okay, so that's the size. So if I actually do like 1010, what's gonna happen? Not integers. So maybe something like this. Maybe that's what we not a tuple. So that's not the way it works. Oh, fixed size, just fixed size. Okay. Float. So it's just gonna say 1010. Oh, now we're looking. Now we're okay. Cool. 2020. So let's do this twice as big. Cool. And what is these? Fig GCA matplotlib fig GCA. Is this the projection that we're seeing? Projection polar. Figure size. Is this what's causing the plot surface? I don't know what's actually causing these, like what is it that's printing these, but like, okay, cool. So now we have these. Now if I add, we add these things, then we're gonna get this fancy stuff in here, okay? So if we add like 100 and 100, now it's gonna do something smoother. It's taking longer, definitely. It's just, I guess. What if shots is 5? Oh god. Yeah, that it doesn't look really smooth. But this is nice. I think that's really nice. At the end of the day, that's really just, I think, what I want to see. And what you kind of see here is that those are not like pointy, right? So those are like quite flat, but they're all, I think, equal. Okay, cool. Now, cool. Mm, how do we do these now? So what did I want to do? I wanted to now play with, so two things we can play. We can play with the animation part of these, which we can try. So I wanted to see if I could like animate, for example, say, that's way less points. If I could animate this part, right? Like map, like what I wanted to do is I want to basically animate that so I kind of shift the start and the stop, right? So let's say start is -2, stop is 2, right? So that's like start, start, that's stop, that's stop. But like I would have that in a loop, and then I would just kind of increase this by 1 and keep reprinting these and see what happens. So animations with matplotlib. Let's see. So simulation of rain. That's not what I want to do. Animations. Oh, something like this. Okay. No, but not like that. I want the whole. I want the actual reference frame to change. That's not. That's probably what I'm looking for. So it's adding the stuff stocks. Okay, and it's just updating the graph. So how does it look like? So creating a subplot, you animate. So animating, then you're getting the data. For aligning lines. Okay, so this is processing the data. Clear the axis. Oh, you're plotting 1 point at a time. Interesting. Maybe that's what we should do. Plot one point at a time. No, but like, I wanted to plot like a sweep at a time. So I definitely need to add these. That's the first thing, right? NumPy is added. Definitely import the animation part. And what I want to do is, yeah, let's just try first separately in a separate cell. So insert cell below. So in the animation, we actually, here is where we're doing the plotting, right? Um, we don't care about these. Fake animate. Create a subplot. So what we need is, we're doing these part. Plot show. So the e values, okay? Until that part. So this is what matters, I think. Okay, and I think the interval is what's gonna make the difference, right? So I'm basically saying, so what I will do is like plus I plus I. So that's kind of shifting, that's shifting the animation. I think that's what it's doing, but essentially the rest is the same. It's just creating a subplot. Figure, plot, figure. That's the figure. So where's the figure here? Plot the surface. Oh, so that's the scatter. That's the scatter, and that's the... Actually, opa, if I just comment these. There you go. Why don't we just try first with the scatter? So does plot have something like clear and show? I don't know. Does this even work? Oh, like... Oh, plot show. So you get a figure at subplot, and this is what you're doing. So this is what you're doing, I think. I think that's the... I think that's the idea. But it doesn't seem to work at all. Print I. Is this printing at all? Anything? This is work. I don't know how this works. Animate. So you give these, you call these with this interval, and then what? And then you're doing these, and then you're getting the values, and then you're plotting the... And next plot. So what if we just... What if we just do it like these? Hmm. Doesn't seem like it's working. Animate in the Jupyter notebook. Yeah, maybe that's not working because of these. Ah, okay. Now we can display this animation object using iPath and HTML display method. Ah, so you gotta do it like these. Okay. Compile the animation. Setting split true will only redraw the parts that have change. Okay, so that compiles the animation. Huh. Huh. So this should actually... Hmm. So you get this stuff, you do this, and then return line, the animation, and then that doesn't return anything really. HTML is not defined. I've got to import these. FFmpeg not available. Okay, so it turns... do I have to do these? Come on. The source code. Get the packages. I don't have to install that. Yeah. Can I not do it? Can I not do like all style and actually run these on a loop? Like, let's say, actually I'm going to use the same thing. So let me just delete these, edit, delete cells. So cool. So the whole thing in a loop, like say I equals 10, right? And then while I bigger than 0, then simulate the thing, do like I++. Does this work? Just in case. And and then, as I said, like no, plus I. So actually I will be 0 until I is smaller than 10, and then that increases. That's better because the I was increasing, so it'll be a never-ending loop. That's nice. But I think so. Because it's gonna be cheaper to do these, I think. What if I just don't do the 3D stuff? What if I just don't do that? for now, and let's see what happens. What? Isn't this how you write? For I in range 0, 10. Just go to hell. Okay, that's printing them. That's printing them like subsequently. Okay, cool. What I want to do is I want to do, so Jupyter Notebook, Python, so clear cell, or clear output within a while loop or something like this. Can I do these? Can I just like clear cell output in code? Yeah, exactly. There you go. So there is a way to do that. There is a way to do that. And I'm going to be clear output way true. Cool. So, and what we're going to do is we're going to plot the whole thing. See what happens, okay? See what happens. Scatter, plot trisurf. What is a plot trisurf? Okay, that's printing these things here. I don't know if these two plots are needed, to be honest. Oh yeah. There we go. There we go. So we're exploring. Nice. So it's actually, is this, are these numbers growing? Wait a second. Yeah, there you go. This is moving. I like it. Okay, cool. It's moving. That's all I need. That's all I need. And now I want to just send like three sort of parallel processes exploring the land of expectation values in the search of the magical barren plateaus. That was a bad joke. Why does it print something twice? Oh, I don't know. Clears the output. It does 10 things. And I really don't like how can I just, do I have to do these? What if I just do that? Don't do that. Oh well, it's not printing anything. Awesome. Huh. I'll have to wait until it stops. Plot the surface. Cool. Can I just hide the color bar? Hide the color bar. So we remove some of these. HB. Yeah. There you go. There you go. Okay, cool. I like it. Now, can we have, so that's from like 8 to 12, the stuff that is plotting in here. Like if I make that bigger, rather than say, for example, 5 and 5, and then 10 shots, but we will get more granular. That would just take too much probably for this to be nice in terms of an animation. Yeah, it didn't take too much just for the first, just to show anything. Oh, I mean, it seems like it's just now starting. I might have to just clean up the memory or just restart the whole thing. But okay, but it's kind of like, yeah. So that's gonna just plot a bigger area, and then exactly. We can try just with one and then see what happens. So, but this is 3D, and then I can have a 2D version of these. Oh yeah, that's just these. That's the beast. Yeah, it's just gonna take too much, I think. It's too slow. So let me just kernel entrapped, and then we're basically gonna, yeah, that's definitely too slow. So we'll keep it to 10, and let's do the same, but like for 2D. So that's 3D, and what I'm gonna do now is I'm gonna insert cell both, and that's gonna be like 2D plotting. So it's gonna be the same. Probably don't even like, probably I don't need like most of the stuff in here, but like whatever. Actually, I should just take all the imports maybe up here as well, and just like, get, remove them from here. And so what this is going to be doing is going to be doing the same, but we're going to have only the alpha parameter. We don't have the betas, we have just the alphas. And then we sweep, blah, blah, blah. We have the eigenvalues, the results, and then, yeah, basically that's what we want. We probably want these here. We don't want these. We don't want these. We don't want any of these. So, but now I basically just kind of, need to rerun that. I just have one parameter, and what if I do this now? Okay, it's breaking. Why is breaking? Well, it's breaking because I need the eigenvalues of, no, the Z operator, that makes sense. But what's the problem? What's the problem? Oh, that's the problem. That's the problem. There you go. It's moving. Okay, cool. So I think I can just do a bit more, right? Like do 100 shots and like and a sweep with like 100. Okay, so here we see how it's exploring, and then it's just the way it is, right? So it's just going to be like that forever. One parameter. So there's no really like much plateaus in here, so to say. But now if we complicate these, because this is the 2D one, this is the 3D plotting. Now if we complicate these, you know what I should do is I should kind of copy that and have a separate, like, just not to have to change the circuit. Insert cell both, and we're gonna do one here, and that kind of can stay for the 3D circuit, which we set like 10, 10, 10, and like I think keeping that this way makes more sense. Is it still gonna run? Yeah, cool. So that's kind of exploring the 3D world. Now, well, the extra twist that we can add to these is that we can add a more complex cost function that is not just these observable, but it's, for example, z plus x, right? So I would so I could also do something like these, right? For example. And then, so this would be like the z eigenvalues, and that would be like the x eigenvalues. But that's even more complicated because, so in this case, I think that's the matrix, right? Exactly. I think that's it, right? Now the problem with these is that it's not defined. So these would be these, this would be these. Exactly. So now the problem here would be that, though, well, we would need the circuits to be executed kind of twice, right? So a sweep for one eigenvalue, and then another sweep for another eigenvalue, and so the e-values would then need to be kind of added up. So you would essentially need to do this will be like a sweep for z, and then you'd have like sweep for x, right? Which is the same, but like it has, so the circuit actually has, oh, that's wrong. The circuit should have a Hadamard gate appended after that. Yeah, that's too much for the video now, I guess. So that would be kind of next step, right? But I like that we can just I like it. So I can just animate that. What if I make a more complex circuit, for example, say here we have alpha and beta, and then we have, like, for example, a layer of like Hadamard. So Hadamard on qubits 1, Hadamard on qubit 0, for example. How does this look like? Does it look good? Looks good. And then we have like an X rotation on beta and alpha, or beta, for example, times 0.2 and alpha times 0.2, for example. Is this doable? Yeah, interesting. So what does this look like? If I now do this, what does this look like? Oh, okay, interesting. That's a complicated place to explore. If I explore like a bigger piece of land, yeah, still should be, I'd like this to be a bit smoother. The thing is I cannot just ramp it up to like 100 because I can really just do, if I do one shot, that's just bad, I think. This is gonna take too much, I think, too much memory. Would be cool to see though. Hmm. Would be cool to see. But I guess I'm not gonna see it. I guess I'm not gonna see it. Oh, what the hell? What the hell? Oh, that's crazy. It's crazy though. Wait a second, what does these mean? So, okay, I'm getting much more granular, but that's like, and there you probably have those plateaus, but like there's nothing in between where this is, it's not so obvious that you kind of see. Like the problem is I can't see sort of in between points, you know what I mean? Unless what we do is we just don't do that, and we just plot the scatter. We just do this, but I guess that's gonna be messy as well. Interrupt the kernel. If I just do it like this, that, no, kernel interrupt. So that just shouldn't be there. That's it. This is gonna be better. Hmm. How can I add like chill music in the background in a YouTube stream? Stream at uh, allow music. So I can choose whatever I play. Create audio library. So you download a track. Okay. So you just do it like that. Okay, here we're just plotting the surface. Yeah, that's pretty crazy. That's just... It's difficult to see. It's really difficult to see kernel interrupt. So what if I just... especially shots one, like that just doesn't make any sense. Like, should actually, you know, which is a 5-5, and then add these here, and then we actually don't plot the scatter, but we just plot the surface. Well, first of all, we can take these away from... No, we cannot take it away from the... No, we cannot take it away from the loop. So, okay, Oh, that looks faster now. Okay, cool. But it's because I'm just doing like 5. Why is it that way? Why is it like this? So I'm just doing 5 steps in between these elements. So if I would do a surface of like, I'll go back to like 2 and 2, right? So what am I doing? What is it doing? Sorry, I'm just getting lost now. So I do between 2 and -2 in 5 steps, in 5 samples. Uh, okay, yeah. Okay, so actually I should just, if I do like these, I probably will see like a much more. Okay, cool. So here you can still see some stuff going on. What I like to do is I like to maybe not like, oh, let's do this. So what if I don't just, what if I don't initialize these? Oh, let's do that. So what if I just do these and so what if I, these are not initialized, these are not emptied in here, and e values is not replaced, but it's added like np append e values, these stuff, right? And what used to be before is just e values equals these. So, but now we're going to comment this out, and we're going to have to, of course, initialize. I mean, this can as well just be, it can just be like these, actually. And I don't need to do that, because that can just still be true if we just initialize it to 0 every time. And now what I do is we initialize these to 0 outside of the loop. And we kind of let the values accumulate. See what happens. So we let the values accumulate because I want to kind of remember the space that I'm exploring, right? Up to a certain value, probably. Am I gonna break stuff? No, nice. Okay, it's growing, it's growing, it's growing. Oh, nice, nice. Okay, so it's yeah. So if I do like 100 steps, now it's growing in all directions, right? So it's getting spikier and spikier. Okay, cool. I wish I had a sense to see where, how is this growing? Like, that's a really rough terrain. Okay, that's already getting close to just like breaking up. But what I would probably do is, like, can I define a max? I'd like to append, but I'd like to kind of like, you know, remove values as well. Oh. Okay, cool. this worked. But yeah, if I keep these, if I just do these here, then I basically, you know, kind of keep exploring, and I just forget what's behind. Um, yeah, I just I really had a good idea with this. I'm really gonna try to improve this a little bit, and then kind of have like a 5 hour live stream on just these going on and seeing whether we find like a barren plateau or something. That would be that would just be fun. But I think, yeah, that's for these. So what if I the kernel entrap? What if I just define, I don't know, a for example, z, and then another hotmart. So there's a circuit. Seems to be a flatter, but still, like, it's hard to see a pattern in here. It's hard to say, yeah, that's easily differentiable. You know what I mean? Like if I accumulate, try to accumulate these things in here, and I say do these like 20 times. No, I mean, I do see a pattern. Okay, there is indeed this pattern arising. Yeah. If I do, can I just say if, can I just plot that as well? It's just doing the whole thing. Yeah, it's fine. Makes no sense. It's making it easy. Ugh. Ugh. Mm-hmm. Yeah, that might as well just be because of these. So if I just have, if I just have these two, maybe gonna. So we just have these two. What are we seeing? Yeah, we're basically seeing that, like, sinus and cosinus style, which, yeah, kind of makes sense, but not, like, if you're complicating the circuit, then I don't know, there's a bit of a pattern in there, but it's just it's not so intuitive that you can just do that. And so the uh, param, parameter shift rule, here they also do not like, so more technical explanation. The transformation n depends smoothly on the parameter, so this kind of function will have a well-defined gradient. The key insight is that we can, in many cases of interest, express this gradient as a linear, but that's not the point. But why? Like these would be so in many cases of interest, right? Like, but not in every case of interest. Let me just tweak that. Let's mean these wall circuit based on do. Thanks. Cool. Yeah. Perfect. I'm gonna finish it. I'm gonna finish the whole thing here. It's been a long video, but it's been a fun one. Definitely a fun one. I'm gonna see if I can tweak that and just let it like run on a live stream. See what happens. It'll be just cool to find a barren plateau. Although with just two parameters, I don't know if it's gonna be possible. But it's just because I can increasing the parameters just doesn't make any sense because you can't just visualize that. I mean, you can visualize just by mapping how the expectation value goes down and whatnot, but like and it kind of converges. But you can't just see like an actual plateau where like you just get into a place where you kind of like move because the derivative is just always, it's not indicating you where to go. Um, cool.